Yet again, have you at any point pondered what our Sun resembled when it was an exceptionally youthful star? The James Webb Space Telescope, JWST, has created a staggering revelation about our Sun. For the first time, we can see our star in an entirely different light. The JWST's most recent disclosure offers entrancing insights into the young periods of stars and the massive cycles that might have occurred in the early stages of our Sun. Have we now opened another of the great secrets of the universe thanks to the new James Webb Telescope? What mysteries still await us out there in the universe? The James Webb Space Telescope is a perfect representation of the advancements made by cutting-edge technologies. Since the telescope was launched, the investigation of the universe has advanced at a rapid pace. With its most recent mission, the JWST has demonstrated its remarkable ability to delve deep into the secrets of the universe once again. The telescope exhibited its ultimate technical superiority when it imaged the object HH21 with great splendor. HH21, also called a Herbig-Haro object, is a very young star, yet advanced enough that it's blowing strong jets into the universe and beginning to shape its surroundings. Since its study by the JWST, the object has provided an abundance of significant data about the youthful phase of stars and, consequently, the early stages of our own Sunday. These observations furnish us with crucial information about the processes that occur during the initial phases of stellar evolution. Herbig-Haro objects are among the most fascinating astrophysical phenomena in regions of young stellar evolution. They consist of narrow jets of gas shot out from newly formed stars and streaming into the surrounding interstellar space at high speeds. These jets collide with surrounding gas and dust, resulting in dramatic emissions. Herbig-Haro objects were discovered in the 1950s by astronomers George Herbig and Guillermo Haro, who were independently studying star-forming regions and initially observed the significant outflows well before the JWST era. The energy-rich jets from the center of a young star are astounding. Who would have thought things would be so violent in the stellar nursery? Young stars are everything but cuddly. They are indeed beautiful but also incredibly powerful. We can barely imagine the forces at play here with our minds alone. The forces that lead to the formation of a star are immense, and even in the initial billion years, things heat up around a young star. It takes countless years for a star to eventually shine as calmly and steadily as our Sun. The object of the latest observations, the Herbig-Haro object HH21, is situated in an active star-forming region in the constellation Perseus, about 1,000 light-years from Earth. HH21 is particularly intriguing as it is one of the youngest and closest examples of these objects, making it an ideal field of study to investigate the physics of star formation in detail. The discovery also provides us with magnificent views of the dynamic processes that likely occurred in the early stages of our Sun's life. The JWST has imaged the Herbig-Haro object HH21 with remarkable accuracy, offering even more fascinating insights into what was once impossible to see. For the first time, it might even be possible to see a double star forming at the center of HH21. The images reveal two brilliant, high-energy jets emanating from a central point. These jets are enriched with particles like carbon monoxide and silicon monoxide and are evidence of high-energy processes within the star and its immediate environment. The discovery of molecular hydrogen within the jets was a major surprise and now provides a completely new picture of the chemical structure and thermodynamic conditions in the early stages of star development. The surrounding accretion disk of the young star, other objects such as planets and moons, might also form. However, the bombardment of the disk by the extreme emissions from the jets could make the formation of stable bodies more challenging. Nonetheless, the JWST studies also showed that the jets of HH21 are slower than those of many other Herbig-Haro objects. This slower speed could indicate that the star is at an early stage of development or that the processes in this young system are generally less tumultuous than in other stellar nurseries. The ability to observe such key cosmic processes up close and with high accuracy represents a significant advancement in cosmology and will lead to ever more exciting discoveries in the future. Observing the birth of new stars also provides insights into how ionized gases and plasma interact. The energetic jets that impact the cold surrounding interstellar medium create radiant shock fronts that act as visual boundaries of the young star systems. These early outflows of a star are akin to the protective shell of our Sun's heliosphere. On a scientific mission with the JWST, researchers are excited about the additional possibilities. The JWST is equipped with a range of innovative scientific instruments, including the Near-Infrared Camera (NIR-CAM), the Near-Infrared Spectrograph (NIR-SPEC), the Mid-Infrared Instrument (MIRI), and the Fine Guidance Sensor (FGS). These instruments can detect even the faintest light from extremely young and distant objects that would otherwise be invisible to our eyes. By using infrared technologies, astronomers can now see through dust clouds to uncover previously hidden corners of the universe and gain direct insights into young stars and their formation regions, often obscured in thick dust shells. Thanks to the high sensitivity of the JWST, astronomers and space enthusiasts alike can enjoy a level of detail that has never before been achieved in the history of astronomy. The JWST can not only image these faint light signals but also analyze them. Never before have scientists been able to see so much detail of the massive jets and precise studies, providing information on the evolution and temperatures of the gases as well as details of all the chemical elements and molecules involved. Herbig-Haro objects, typical of dynamic star-forming regions like the Orion Nebula or the constellation Perseus, are valuable for studying chemical processes in space. These regions are rich in gas and dust, offering ideal conditions for star formation. Stars are formed from the accumulation of these collections of matter influenced by massive forces. The jets ejected by young stars, which travel through space at velocities of several hundred kilometers per second, are just part of the dynamic processes that occur during star development. When these jets impact the surrounding medium, they heat it up and create the characteristic brilliant arcs and clusters visible through our telescopes. Within this vivid display, enormous physical forces are at work, as well as a light show of the elements along with electrical and magnetic forces. Captivating observations reveal how the jets interact with the surrounding material, helping to shape the cloud from which the star is formed. Each beam of light and each color gives the JWST and thus the scientists valuable clues about what is happening here. Observing these processes live and in their early stages is like getting a direct glimpse into the blueprint of a star. If we understand how matter is integrated into the cosmic circle, how the final mass of a star is determined, and which elements and gases are involved, we can draw significant conclusions about the forces at work. This, in turn, helps us understand the overall matter formation processes in the universe. Although we can imagine that star formation is one of the great energy processes known to humankind, it is hard to grasp that such a young star can produce winds extending several hundred light-years and blow them into space. The jets of the Herbig-Haro objects could be direct remnants of the tremendous angular energy that causes dust disks to begin to rotate and coalesce in the center. Nonetheless, it is possible that the young star uses the jets to expel the forces it no longer needs while simultaneously driving developmental processes in the gas and dust cloud and star systems. So far, we have only observed jets in young and actively forming stars. However, we also know of very old galaxies in the universe that produce powerful jets in their active centers. Some of these cosmic winds extend far beyond their galaxies. These winds likely also disperse enormous amounts of material, which ultimately influences the mass of the star and the environmental conditions of the star-forming region. The material and energy expelled then drive further star births or other elements in the universe. Let's consider for a moment the role of magnetic fields around a young star. Magnetic fields are crucial for controlling the accretion process in which the star attracts gas and dust from the surrounding disk, and they also influence the direction of the jets. Magnetic fields are not only significant in the immediate vicinity of young stars but are present throughout the universe. These invisible forces direct the paths of charged particles and influence the shape and development of entire star systems. In our own solar system, the magnetic forces mediated by the Sun's magnetic field are essential for maintaining the heliosphere, the bubble that protects the entire solar system from harmful cosmic rays from interstellar space. The Sun itself generates a complex and variable magnetic field that determines the order of our solar system, influences planetary atmospheres, and regulates space weather patterns. Sunspots, solar flares, and coronal mass ejections are signs of the Sun's magnetic activity. As you might know, such events sometimes significantly affect the operation of satellites and communication systems on Earth and produce auroras. The study of magnetic fields and young stellar systems like HH21 is an exciting field of research and is still in its early stages. If we understand the development of stars in distant regions, we can also gain insights into the history of our Sun. Our star is 4.5 billion years old and has undergone many changes since its birth in a cloud of dust and gas. The beginnings of the system also determined how planets were formed, from the solid Jupiter to the rocky planets including our Earth, various gas giants, and small planets like Mercury or Pluto. They were all somehow present in the early stages of the system, or their distinct conditions helped shape the formation of the planet and consequently the vast environment. The James Webb Space Telescope, JWST, continues to redefine our understanding of the universe with each new discovery. Its advanced infrared capabilities have already provided unprecedented insights into star formation and the early stages of cosmic evolution. The ability to peer through dense dust clouds and observe hidden processes is revolutionizing our knowledge of how stars and planetary systems form. Observations of protoplanetary disks, where new planets are born, are shedding light on the conditions that lead to planetary formation. The JWST's detailed imaging and spectroscopy allow scientists to study the composition and structure of these disks, offering clues about the types of planets that might form and their potential habitability. The study of distant galaxies and quasars is also benefiting from the JWST's capabilities. By analyzing the light from these far-off objects, astronomers can trace the history of cosmic evolution, from the formation of the first galaxies to the development of large-scale structures in the universe. This research helps us understand the distribution of dark matter, the expansion of the universe, and the conditions that led to the formation of galaxies and stars. One of the most exciting aspects of JWST's mission is its potential to answer fundamental questions about the origins of life. By studying the chemical composition of distant planets and their atmospheres, the telescope might help identify signs of habitability or even extraterrestrial life. This search for life beyond Earth is one of the ultimate goals of modern astronomy and astrobiology. The JWST also serves as a testament to human innovation and collaboration. Its construction and deployment involved contributions from thousands of scientists, engineers, and technicians across multiple space agencies. The telescope's success highlights the power of international cooperation in advancing our understanding of the cosmos. As the JWST continues its mission, it will undoubtedly reveal even more about the universe's mysteries. Its discoveries will inspire future generations of scientists and researchers, pushing the boundaries of our knowledge and expanding our view of the cosmos. The telescope's data will also inform future missions and ground-based observations, guiding the next steps in our quest to explore and understand the universe. The James Webb Space Telescope, JWST, has opened new avenues for exploring the universe by delving into regions and phenomena that were previously inaccessible. One area of focus is the detailed observation of cosmic dust. JWST's infrared capabilities enable it to study the properties and distribution of dust in various cosmic environments, such as star-forming regions and the interstellar medium. This research is crucial for understanding how dust influences star formation, galaxy evolution, and the chemistry of the universe. Another significant contribution of JWST is its investigation into the formation and behavior of black holes, particularly in the early universe. By observing the growth of supermassive black holes and their impact on surrounding galaxies, scientists can gain insights into the mechanisms driving their formation and the role they play in cosmic evolution. These observations help refine models of black hole accretion and the feedback processes affecting galaxy development. JWST's capabilities also extend to the study of cosmic voids, vast, empty regions between galaxy clusters. Understanding these voids provides insights into the large-scale structure of the universe and the distribution of dark matter. By mapping the density and distribution of galaxies within these voids, researchers can test theories about the nature of dark energy and its effect on cosmic expansion. The telescope's observations of star clusters, particularly in their formative stages, offer valuable data on the dynamics of cluster formation and the interactions between stars within these dense environments. This research sheds light on how clusters influence the evolution of individual stars and the distribution of stellar populations in galaxies. Additionally, JWST is examining the formation and dynamics of galactic mergers. By studying how galaxies collide and merge, scientists can better understand the processes that drive galaxy growth and shape their structure. These observations provide clues about the history of galaxy formation and the role of mergers in creating the large-scale structures observed in the universe today. The JWST is also focusing on the search for water in various cosmic environments. Water is a key molecule for understanding the potential for life, and its presence in diverse settings, such as on exoplanets, in star-forming regions, and in the early universe, provides essential information about the conditions that might support life. In the realm of stellar astrophysics, JWST's observations of binary star systems, particularly those involving one star as a compact object like a neutron star or black hole, are revealing new details about the interactions and material exchange between these stars. This research contributes to our understanding of stellar evolution and the formation of exotic objects in the universe. Overall, the JWST's advanced instruments and observational techniques are driving a deeper exploration of the universe, revealing new insights into its most fundamental aspects and continuing to push the boundaries of what we know about cosmic phenomena.